Hello and welcome to week 14 in artificial intelligence. This week we're going to talk about two pretty compelling topics. First, we're going to talk about natural language processing from a deep learning perspective, so applying deep learning to do natural language processing. The second topic will be a bit more of a generic conversation around computer vision. And we start off having to learn a little bit about vision in general. Moving on to our agenda, we'll talk a little bit about the assignments, as we always do. We'll talk about Chapter 24, Deep Learning for Natural Language Processing, and then we'll move into Chapter 25, which centers on computer vision. First, the assignments. As I mentioned, into week 14. This week, your natural language processing project is due. So spend some time doing some natural language processing. And as always, try to make it interesting but attainable. Make sure that you have sent your requests prior for approval. Don't just do something, make sure you get approval of your topic first. So in part, I can help you be successful. Some of the assignments have been a bit off target. So hopefully sending that approval ahead of time, we can avoid that going forward. Also keeping in mind that robotic simulations is coming up the week after, week 15, and then we move into the final week with your test. Project 4 centers on natural language processing, as I mentioned, so select a topic of personal interest, find some tools, libraries, and code as a starting point. Make sure that you give a reference to that starting point and make sure you change it somewhat. And then you can use something like Jupyter, Anaconda, Azure Databricks, or any other alternative environment that does natural language processing, assuming you get approval prior. And then the grading, as always, is spread amongst the items outlined below. 10% does come from having asked for and received approval for your topic, so make sure you do that part. The discussion for week 14 is to define natural language processing and then describe a practical application of the technology. So an example that maybe you've seen in the real world of use of this technology, something that you've observed, something you think is pretty cool, and as always, remember to reply to your classmates. Here's some references that are useful in this course. They're the same ones that we used along the way. There are some topics in here that might be relevant in your assignments, so you might want to take a look. Moving on to chapter 24, which centers on deep learning for natural language processing. We start off with a conversation around word embeddings. So what is a word embedding? And the basic idea is you want to take a word or a series of words and turn them into numbers, because computers do better with numbers than they do with strings. It's just kind of the nature of things. Your simplest approach would be to use a one-hot vector, which basically you would end up with a really big, very sparse vector. So you would basically turn on a bit if a word was present inside of a sentence, and then if it's not, then it wouldn't be. So because we don't use most of the words in our language or our vocabulary all the time, it would be incredibly sparse. Not a good idea. So instead, what we do is have an algorithm that essentially learns the vector from the data, and then it uses that approach that it learned to represent things going forward. An interesting characteristic of those sort of approaches is that the words that are close to each other within the domain also are close to each other within the representation, and so in the n-dimensional space associated with that vector. The link on the screen is pretty interesting, and you can see the result of it here. And so you can kind of tell that I've selected the cities, the countries. In this case, I selected France, and you can see that the nearest points to France happen to also be countries. So it's a pretty interesting sort of characteristic of a word vector that they are organized close together to where things that are similar things show up together in a similar way. This isn't being done necessarily purposely. It's something that is kind of a side effect, and to some extent, we don't know exactly why it occurs, but it does have some very useful characteristics. In part, things that are similarly related do show up to be close together. Recurrent neural networks are something we've talked a little bit about in the past, and they turn out to be quite useful inside of natural language processing. While there are some challenges associated with their use, lots of clever ways have came up with to accommodate or circumvent those challenges. So The basic idea here is to talk about the language models with recurrent neural networks. So a language model is a review is basically a way of figuring out from a sequence of words the words that are going to potentially come next. It's a probabilistic distribution over a sequence of words, and it enables you to predict the next word based upon the previous words. And we kind of do that ourselves if you think about it intuitively. Whenever someone's talking, you kind of know what's coming. At least you should, unless you know they're taking a random sort of detour. Uh, Feed-forward networks struggle with asymmetry, so things like him and they, whereas recurrent neural networks process time series data one at a time, so they handle such things a bit better. Recurrent neural network language models essentially convert those or input each word as an encoded word embedding vector, and the output is essentially a distribution of what the next possible words could be in the sentence. So it's a probability or confidence associated with those words that are coming next. Classification is an important aspect in general with recurrent neural networks, in particular with natural language processing. We use recurrent neural networks to do things like parts of speech tagging and the determination of the him sort of context of who took him to the hospital, right? And we may also use something called a bidirectional neural network, which is something that allows you to kind of essentially go backwards and forwards in time. Sequence to sequence models are pretty powerful as well. That's part of how we do things in the realm of machine translation. It's essentially a way of mapping from source to target, as we talked about last week, being able to go from Spanish to English or English to Spanish, and it's doing so in a more intelligent way than trying to just do words at a time. So instead, you have a sequence of things that you're mapping to another sequence. There are some challenges with using recurrent neural networks with machine translation. In part, there's things like nearby context bias, which basically means the words that you've seen more recently have more importance potentially than those that are further away. That's not necessarily the case whenever you're dealing with language. And also there's this concept of fixed context size limit. So you may need to deal with fixed dimensional hidden space vectors and so on, hidden state vectors and so on. And they're also potentially slower because they're potentially word at a time approach. You can't necessarily do parallelism, although a lot of these are addressed through the use of something called attention sequence to sequence models. I'm not going to go into a whole lot of detail on it. The key thing to take away is that recurrent neural networks are very useful whenever you talk about machine translation. Pre-training and transfer learning, we talked a little bit about last week. The basic idea here is that sometimes it's very challenging to come up with this corpus, and you need a labeled set of data in order to do training, because we're doing supervised training here. That's a key concept to understand, is that you're being given input that is a series of words or a series of words with potentially parts of speech or whatever it might be. Having something that is pre-trained allows you then to take that information and augment it with additional information through transfer learning. So you're able to essentially kind of refine the end layers of the neural network is what you're basically doing to adjust the weights near the outside, near the end of it. The key things that it does is first makes it to where you can potentially get it done a whole lot quicker. More importantly, it also handles the case where you may not have as much data to work with. You'll probably see the GloVe model if you do much research on this domain. It's around global vectors, and it's a very well-known pre-trained natural language model that is used in lots of domains. And then there's this concept of a contextual representation, which goes a little further than even the pre-trained models with of words to basically going also out to context as well. Now I thought I would share kind of a real-world example of a project that I'm currently working on. So I'm part of a team that's constructing an automatic speech recognition system that has the intent of not just recognizing speech, but actually producing transcripts of meetings, essentially. So imagine you have a a school board meeting, and you have people that are there. You've got people that are on the board that you know who are always going to be there. Plus, you may potentially have people that are showing up to talk about something. At the end of those experiences, somebody has to take some notes. Sometimes it's as simple as there's a scribe who writes down what occurs. Sometimes you actually need to have a proper transcript depending upon what all was going on. Say the meeting wasn't just an average meeting, but maybe they were deciding on disciplinary actions of a instructor or teacher. In that situation, you've got to have likely a record of the things that went on to justify why the decisions were made. The end of all that is to have somebody that does that work is potentially quite expensive. Computers are pretty good at such things, so the idea here is to enable a computer that can basically do that work for you. Listen to the conversation, write down the transcript, including who's speaking. The approach that we're utilizing on this project is an ensemble-based approach. All that means is that we're tying together kind of the best of the best. We're taking lots of different models, lots of different approaches, using them together with the intent of creating a better thing than the individual parts. So it very much is the sum of the parts is greater than their individual, or the sum of the whole is greater than the parts. So the basic approach that's going on is you convert from the utterances, the actual sounds, using an acoustic model, then you layer a language model on top of that. And then you, after the language model, you actually are converting those words into sentences essentially. And then after that, you apply natural language processing to turn that into something that's more human readable. So you're going to insert punctuation. You're going to know when sentences start and stop, potentially introducing things like capitalization, proper nouns, all that kind of stuff. And then a little stuff like converting numbers to words or words to numbers. So whenever you say 2021, we want that to be 2021, right? And if I say 2021, even if what the typical ASR system is going to output is going to be the words, not the numbers. So that's why you have to do that sort of work later on. There's lots of other things that go along around the way, biometrics to figure out who the speaker is, diaritization to figure out who's talking when, and so on. But the key takeaway here is that using these technologies and applying things like natural language processing on the end of it, we're able to do something that basically a person does. So it's a pretty compelling topic. Chapter 25 centers on computer vision. And again, whenever I was in my master's long ago when the dinosaurs roamed the earth, I took a course on computer vision at a master's level. So this is a topic that is far beyond what you could cover, in a lecture of a 16 or week semester class, right? So in general, we're going to be hitting the high points, kind of the things to take away, giving you a feel of the domain without really drilling into it at a great depth. So to jump into the first section, which is the introduction, the key things to take away from the introduction is around the concepts of active versus passive sensing. And this is a generic concept, but it's obviously very applicable to computer vision. Whenever you're doing passive sensing, you're not emitting anything. You're just observing what's already out there. If you think about it from a submarine perspective, whenever a submarine is listening passively, they're not emitting any sounds. They're just listening to what's out there. You're observing, but without interfering or causing any kind of interaction with your domain. When you switch over to active sensing, you're sending something out and expecting to get something back. So it may be as simple as shining a light and then seeing the result of that light illuminating things. And you might want to do that so that you know where the light source is, because sometimes it can be challenging in computer vision to know where the light is coming from. And the light and shadows can actually cause you a lot of challenges in computer vision. But more likely with especially the current sort of approaches is going to be things like radar and ultrasound, where you're basically sending out something like radar and expecting to get back something, or sending out potentially even sound in the case of something under the water and you're expecting to get something back. That's whenever a submarine does a ping, they're sending out a sound and they're waiting for the things to bounce back so they can get a better sense of that. In the case of a submarine, you don't do that because you don't want people to know where you're at. But if you're an autonomous agent roaming through, a domain, probably doesn't matter unless you're being used in warfare. A feature is something that you derive from an image. So it's something of interest inside of that image, and you do feature extraction to get those features from the image. So it's basically some sort of representation of something of interest inside of that image. Generally speaking, your images are going to be two-dimensional as well. We'll talk about that in a moment. There's kind of two basic approaches to vision. One is more of an object modeling approach, which is all about geometric figures and trying to model things geometrically. The other is more about rendering, and it's kind of, to some extent, you can think about ray tracing. It's kind of that kind of concept. It's a combination of physical, geometric, and statistical processing, lots of fun math, calculating angles, and all kinds of good stuff like that. But the basic idea is those are the two big categories of approaches to vision. And we'll have one more, but there's reconstruction, which is the idea of taking what you're observing and then building a model of it, and then potentially presenting that model in some slightly different way. Recognition's about being able to detect things, find things, see where boundaries are between things, notice that they're present. A visual representation of that recognition is to see something and be able to identify what those things are. And this is actually pretty easy to do. If you take a look at Azure's Cognitive Services API, there's a web page where you can go to and basically just upload an image, and it'll tag the things in it. And also show you the JSON that comes back. I uploaded a picture of a cow by a pile of hay with my wife in the background and so on. And it basically told me that, yeah, here's the cow. And it did correctly identify the cow with a bounding box. We'll talk about that in a moment. And it also told me that the cow was standing on hay because there was actually hay underneath, and it noticed that there was hay in front as well, and so on. So the point of that is being able to see something and notice it and know what it is. And then there's a corresponding tagging, and you can see on the diagram the bounding boxes of the model that it observed. And also reorganization of potentially changing those things around in a slightly different way. So how do you get an image? And that's kind of a key concept. What is an image and what is image formation? So again, basic concepts. You have image sensors, or things which capture images from a scene and capture objects in a scene and convert it into an image. Generally speaking, 2D image, even though we may end up taking two pictures in stereo, but it's still typically one image is going to be two-dimensional. It's basically a big vector or a big matrix of pixels. And a pixel is, generally speaking, the smallest element of a sensor. And a sensor is made up of a collection of pixels. And whenever you buy a camera and you talk about 20 megapixels, what you're talking about is 20 million pixels in the sensor that is taking the picture. Some of the cameras now are going up to pretty amazing levels of pixels. I believe my wife's new phone was 100 and something megapixel, which is pretty amazing that you're packing them in that tightly. Generally speaking, there's going to be a lens involved, so there's going to be some sort of optics going on with this image capture as well. Yes, there are other types of imaging that can occur, such as pinhole cameras and so on, that your text talks about. Almost everything today has some form of a lens in the mix. A camera has a lens, generally speaking, and sometimes that lens can change in zoom, so you can have optic zoom as well, and changing what is in focus and how far out. There's typically a focal plane. That's where the sharpest image is going to reside, and there's also a depth of field, which is the range of things being in focus within the image. So if you go outside of that depth of field, it's going to get blurry. Ambient light, the general light within the domain. Diffuse reflection is this concept that whenever light hits something, it bounces off in a diffuse way. It doesn't stay focused, it scatters. And then when we talk about colors inside of images, we're typically measuring them in red, green, and blue, so RGB values, so that your intensity of each one of those elements together combines to produce essentially the color of a particular pixel. So we've talked about what features are before, which is something of interest inside of an image. We talked about how you capture an image. So let's talk a little bit about what are these kind of simple image features that we might be interested in. First of all, edges and lines and boundaries are typically something of interest. We kind of need to know where things start and stop. They're oftentimes either straight or curved. That kind of covers most things. I guess it could be jagged or something, but generally speaking, it's a crisp boundary where there's a significant change in the brightness or the nature of the thing you're observing. The texture is essentially kind of relates to the surface of the object or a pattern. It can be kind of inferred oftentimes based upon the image and patterns that occur inside of the images, what light it gives off in what ways. Optical flow relates to things that are typically in motion. So you take a series of images and you look at one after the other, like a motion picture. You can tell how something is moving based upon the flow of those images, especially given you know the time between the images, most likely. Segmentation is kind of similar to detecting images, but it's more about breaking similar pixels into groups, into regions, so that you can then identify kind of related to edges and boundaries, but at a higher level. And generally speaking, a segmentation is going to definitely have an edge involved. An important characteristic too is also to be able to classify images. We do this quite a bit, and actually it's one of the more successful parts of image processing that we've seen lately. Again, if you take a look at the Cognitive Services API outside of Azure, it does a fair amount of image classification. It does so doing more pattern recognition. We'll talk about that in a moment, but it's basically around being able to find an object in an image. So looking for something that exists inside of it. And you kind of take a look and you try to find things like fire hydrants or stop signs if you're doing a self-driving car. So it's all about looking at an image and trying to find things. A scene can also contain multiple objects that work together into a real world setting. The example I gave earlier of an image of a cow standing next to a pile of hay, that is, that all goes together to form a whole scene. So it's outside, it's on the ground, there's hay involved, the cow may be standing on the hay or whatever, and it may even speak to the color of the cow. A brown cow is eating hay outside. That defines the scene. Convolutional neural networks are really good at this. They do a good job at classification. In part, that's kind of how they came to be. Convolutional neural networks got their start with digit recognition back in the early days of neural networks really taking off more recently. And it came back to whenever somebody writes a zip code on a letter, being able to accurately classify that and sort it automatically is really important. So that's where it kind of comes from. Data set augmentation is an approach that you take where you'll take a labeled data set and manipulate it slightly. You might scale the size of the image, you might shrink the images, you might rotate them, move the image around, maybe cut it off, lots of different things with the intent of making it so that essentially the convolutional neural network sees different patterns beyond what it might see otherwise and is able to learn better. Context is important in that it helps us know what we need to look for. So if you know that you're outside, you're not as likely to expect to see something like a recliner, although that could happen. But the context of an image is very much about giving you a sense of what it is that you might be seeing or should expect to see or what you should look for. So that's where this concept of detecting images comes from. We've talked about classifying them, of given this image, this region of an image, what does this image have in it? So detecting images are going to be very much about using something like a box or a sliding window to scan an image looking for things. And then when you find it, put a bounding box around it. Just as we saw on the beginning of the dinosaur with a box around it, it's that kind of concept. It highlights the area where the thing is known to be. That also comes in handy if you start looking at things like motion over time to see if that thing is moving, right? We typically use things like sliding windows to figure out where it is, and we start using classifiers to try to classify the window. That ends up where you have multiple hits potentially, right? Of you slide the window across, and maybe the image that you're classifying, the thing that's inside of that, the feature that's inside of that image that you're classifying, occurs multiple instances, you're going to pick one of them, maybe the one that has the most centric sort of characteristic or whatever mechanism it will be, but you don't necessarily want to pick all of them where it shows up, because it may very well be quite a few. So you'll pick one near the where it's centered across the image, basically, or the feature of interest. The 3D world is kind of challenging because, again, all these things we've talked about have been in 2 dimensions, right? We've got essentially a matrix of pixels that we're interacting with. So in order to deal with a 3D world, we have to do some stuff. And part of that is potentially having multiple cameras taking pictures of the world at the same time. That's where this kind of concept of a binocular sort of view onto the world, just as people do. We're able to take 2 images, compare them in our brain, and determine depth based upon that. And so can computers. They look at it from their perspectives, which is what the diagram is showing you. And then from those things, knowing how far apart things are, you're able to determine what it is, the shape of the thing you're actually looking at is. So you could do the same sort of thing potentially by taking multiple pictures and moving through time, but that's problematic in that the thing you're taking a picture of could move as well. So if you take 2 pictures or more at the same point in time, and you compare those, then you can make a good estimation of what it is the world really looks like that you're looking at. You can do something similar, as I just mentioned, with taking multiple snapshots over time and comparing them as you move through. Problematic if the thing is in motion, or maybe there's obstructions that occur as well. So you have to do a fair amount of inference. But sometimes this is where things like the Kinect that Microsoft came up with a while back for their Xbox had multiple cameras for observing a player playing a game. And it was able to do pretty good identification of location, motion, and so on, because it mirrored the idea of having 2 different eyes and comparing them and doing inference as it was observing. So that's the basic idea of when you're dealing with the 3D world, you have to somehow create basically a set of models to approximate what it is you think the real thing exists. And you're going to be doing so, as I mentioned early on, either using some sort of likely a ray tracing sort of approach, or you're going to be using a geometric approach, or you may be using a combination of the two to figure out which one of these things matches up to the thing that I'm observing. And these become very relevant whenever you start doing things like plotting motion and such across domain. And with that, we've done a very brief introduction of computer vision and using natural language, or doing natural language processing inside of deep neural networks. As always, if you have questions, feel free to reach out to me. That's what I'm here for. So shoot me an email, text, whatever it might be. I'll get back to you as soon as I can. As always, stay safe, and I will speak with you next week.